Welcome to AI Paper Podcasts, where we break down the latest research-making waves in the AI world. Today, we're looking at a really interesting paper that pushes multimodal large language models, MLLMs, to do more than just see images. We're talking about models that can actively, dynamically, think with visual info.
Yeah, it's a pretty significant step, actually. We're kind of used to MLLMs just describing what's in a picture, but this work lets them really dig in, interrogate the image using code, to solve some quite complex problems. We're talking about the paper Thyme, Think Beyond Images.
Exactly. And for those of you maybe short on time or wanting the quick takeaway for your work, here's the essence of Thyme in about a minute. Okay, first insight. Thyme brings in this whole new paradigm for MLLMs.
Yeah.
It gives them the power to autonomously generate and then run code for all sorts of image processing, things like cropping, but also rotation, contrast changes, and even pretty complex math calculations. That's pretty new for open source models.
Right. And second, this isn't just about using preset tools. Thyme really goes beyond those older think with images ideas because it allows manipulation, on the fly. The model has a lot of autonomy in deciding when to use an operation and how to do it. That makes real-time dynamic decision-making possible.
And third, how does it get there? Well, it's built on this quite clever two-stage training strategy. You've got Supervised Fine-Tuning, SFT, first to teach the basics of code generation. Then it's followed by reinforcement learning, RL, using a new algorithm they developed called GRPO-ATS. And that's specifically designed to really sharpen the decision-making and make sure the code it writes is, valid and actually works.
And the payoff, the fourth key insight, is in the results. They're really quite compelling. Thyme shows the significant, consistent performance boost across nearly 20 different benchmarks. We're seeing big improvements in areas like high-risk perception, complex reasoning tasks, and it often outperforms even bigger models.
So if you're an AI researcher, an ML engineer listening to this, the takeaway is pretty clear. This paper gives you an open source framework. It brings dynamic, interactive visual analysis to MLLMs. It's like empowering these models to act like a seasoned analyst with a whole digital toolkit for visual data.
Yeah.
Okay, so let's dive deeper. What were the specific problems that Thyme was really aiming to fix?
Well, yeah, before Thyme, MLLMs trying to work with images, they hit some pretty major roadblocks. One idea was this thinking with generated images, maybe drawing extra lines on an image to help reasoning. Conceptually cool, maybe, but practically, it kind of struggled. You had issues with image quality, fine details getting lost, and it was computationally heavy, slow.
Right. I remember seeing some of that work. And the other main approach, thinking with cropping.
Yeah.
Useful, sure, but limited. It was mostly just outputting bounding boxes for simple crops, right?
Yeah.
Help with perception sometimes, cut down hallucinations maybe, but yeah, pretty basic.
Exactly. And you already had proprietary models like OpenAI's O3 doing much more sophisticated things. So there was this gap. No open source model really combined rich image manipulation and boosted logical reasoning using code in the same way.
Okay, so that's the gap Thyme steps into with this think beyond images idea. What are its core principles then? What makes it different?
So it's really built on overcoming those limits. First, rich functionality. It's way beyond just cropping. We're talking scaling, rotating, fixing contrast, and doing complex math. That whole range of tools, that's a huge thing for open source MLLMs.
And the autonomy part sounds critical. It's not just taking orders, it's deciding if it needs to do something, what to do, and how, by writing the code itself.
Dynamically. Precisely. That self-direction without a human stepping in for every little task, that's a major leap forward for these models.
No. And they managed to train this efficiently. I saw a note about the SFT stage.
Yeah, that's pretty impressive too. The end-to-end training is designed to be efficient. The paper mentions the SFT stage, the part that unlocks all these functions, only takes about 200 GPU hours, which, relatively speaking, is quite fast to enable such a wide set of abilities. Then the RL stage builds on that.
And the results back it up. Consistent improvements.
Yeah, across the board, the paper shows really significant, stable gains in perception, reasoning, general tasks, across, I think, all 20 benchmarks they tested on.
Okay, so that's the vision. Sounds powerful. How does it actually work? Let's get under the hood. The paper talks about this pipeline, this interaction between the model and something called the sandbox. Can you walk us through that? It seems crucial.
Absolutely. It all starts with the user's input, a question or a task. The model first generates some high-level reasoning, its plan. Then, depending on how hard the problem looks, it decides, okay, do I need code here or not? If not, simple enough, it just gives a direct answer.
But if it does think code is the way to go, it writes it itself. And not just a generic template, right? It figures out the specifics, like the exact crop coordinates or the contrast level.
Exactly. It determines all those parameters, the contrast factor, the crop box details, the zoom level, whatever's needed. That level of autonomous detail is, really powerful.
Okay. And that code, whether it's for image stuff like cropping or zooming or for math, it gets run in this sandbox.
That's right. The generated code goes into the sandbox for execution.
The sandbox. Sounds like Thyme's secret sauce, maybe. What's its main job and how does it actually help the model code better? That seems like a key interaction.
Yeah, you could call it the secret sauce. Its main purpose is simple: securely run the code the model wrote and send back the results. Security is built in. It spots and skips dangerous commands like file deletion, stuff like remove or unlink, and it puts a hard stop, a 10-second limit on how long any code can run.
Okay, so it keeps things safe. Makes sense. But the part about helping the model code, how does that work? A sandbox assisting the AI.
This is where it gets really smart, especially for smaller models, say the 7B parameter ones they used. These models can often stumble on, minor coding stuff. Formatting, indentation errors, basic boundary checks, like if a requested crop goes outside the image boundary. The sandbox just handles that stuff automatically. It uses tools like AutoPip8 to fix formatting, and the ASMAST module, the Abstract Syntax Tree module, to correct boundary errors for image operations.
Ah, I see. So the sandbox basically takes care of the common fiddly coding mistakes. It lets the model focus on the bigger picture, the reasoning, the problem solving, instead of getting tripped up by a misplaced bracket or an off by one error.
Exactly. It smooths out the process. It even presets things like the image path variable and imports common libraries like CV2, making the model's job even easier. And crucially, for conversations that go back and forth, it remembers the context. It tracks variables across multiple code executions within one chat. So yeah, it's not just passively running code, it's an active partner, maintaining continuity, making the whole multi-turn interaction much more reliable.
Okay, that clarifies the pipeline.
Okay.
So you have this model generating code and this smart sandbox running it. How do you actually train an MLLM to do this, to think beyond images? The paper mentions a two-stage process. Stage 1 is supervised fine-tuning, SFT. They call it the cold start.
Yep. The SFT stage is about building that initial foundation. They put a lot of effort into the data. They curated about 500,000 high-quality samples, filtering down from over 4 million raw examples. And they structured this data by complexity to guide the learning.
Right, starting simple with no-code samples where the model just answers directly, then moving to the real-world time data that actually needs code. How did they ensure that data was good, the code requiring stuff?
They were pretty rigorous about it. First, the sandbox itself acted as a filter, tossing out any code that just wouldn't run. Then they used another large MLLM, Qwen 2.5 VL72B, as a kind of checker to see if the code actually achieved the goal. Like, did it make the text clearer? And finally, human experts did a final careful review. That whole process resulted in about 50,000 really solid, executable question-answer pairs where code was needed.
That's quite a filtering process. And they realized real-world data might not cover everything, so they also manually created data for specific skills, like rotation. What was special there?
Yeah, the rotation data is interesting. They didn't just rotate images randomly. They rotated them between 30 and 335 degrees and then trained the model to generate the code needed to fix it based on the known ground truth angle. This is important because MLLMs usually aren't great at handling rotation unless you tell them the angle. This data teaches the model to figure it out and correct it itself.
Okay. So directly teaching the correction skill. And they did similar things for low contrast, cropping based on ground truth boxes, and even computational code using math datasets.
Exactly. For the math stuff, they used specialized datasets and even leveraged models like Gemini 2.5 Pro to generate chain-of-thought reasoning, and then GPT-4o to refine that into leaner executable code.
And the multi-round conversation data seems key too, for learning how to fix mistakes or improve on a previous step.
Definitely. That iterative refinement is crucial. For the SFT training itself, they had some specific strategies, like train on last round only. For those multi-turn chats, this stops the model learning potentially bad habits from earlier, less optimal turns. They also mask the sandbox output during training, so the model learns to generate the code, not predict the result of the code. And for the math data, because it was smaller, they used math data annealing, basically training it separately with a lower learning rate so it wouldn't get lost amongst all the image data.
Okay, makes sense. That's the SFT cold start. Then stage 2, Time reinforcement learning. This sounds like where the model really learns to make smart decisions, especially with that GRPO-ATS algorithm you mentioned earlier.
That's right. RL is about refining the behavior, optimizing the decision-making, and again, data was key here. They used public data sets, but also added 10,000 manually collected high-resolution images. These specifically had tiny objects, things taking up less than 5% of the image area, really hard stuff to spot. The goal was to push the model's perception on really challenging, realistic tasks.
And a whole team of human annotators created questions for these images, covering OCR, object recognition, chart understanding, all sorts. That sounds like a massive effort.
It really was. 15 annotators, cross-checking, expert review. They clearly invested heavily in high-quality RL data.
Okay, so on to the algorithm, GRPO-ATS. What's the core innovation there? You mentioned precision versus exploration.
Exactly. The motivation is this tension. Generating code needs to be super precise, almost deterministic. One wrong character, it breaks. But generating natural language reasoning, you actually want a bit more flexibility, some exploration of ideas. Using the same approach for both isn't ideal. High temperature or randomness is bad for code.
Right, so how does GRPO-ATS solve that? Adaptive temperature.
Yes, adaptive temperature sampling. It's pretty neat. When the model starts generating code signaled by the code token, the temperature drops to 0. Purely deterministic output. Maximum precision, minimum errors. But when it's generating the text parts, the reasoning, the temperature is set higher, like 1.0. This encourages more diverse phrasing, exploring different ways to explain its thinking. It swishes dynamically. See code, temp 0. Finish code, block. Back to default temp.
That's really elegant. It's like switching tools at precision laser for code, a broader brush for language. What are the big advantages of doing it that way?
Two main things. First, sample efficiency in RL. Bad code makes training samples useless. By ensuring code is generated precisely, more of the samples are actually valid and help the model learn. Second, it stops the model getting scared of writing code. Because code is tricky and error-prone, an RL model might just learn to avoid it altogether if it keeps getting penalized for mistakes. The zero temp for code prevents that.
Keeps it using its superpower, essentially. Okay, and like any RL setup, the reward function is critical. How did they design the rewards to encourage the right kind of behavior?
They used a combination of three things. A formatting reward, basically. Does the output follow the structure, using the right tags like think and answer? Then a result reward, does the final answer actually match the ground truth? They use rules for simple cases, and another MLLM to check semantic meaning for more complex answers. And finally, a consistency reward, does the answer logically follow from the reasoning steps the model laid out in the think part.
Okay, result and formatting seems standard, but the consistency reward is interesting. How do they combine these? Especially to avoid rewarding a model that's, say, consistently wrong but logical in its wrongness.
Ah, good point. They use a specific weighting formula. The final reward is result reward x, 1 plus 0.5 x consistency reward, plus 0.5 x formatting reward. The key is multiplying the consistency bonus by the result reward. This means consistency only gets rewarded if the answer is actually correct. You don't get points for being logically incorrect.
Clever. So correctness gates the reward for consistency. And they found this worked better than just rewarding the thinking process or rewarding any code execution.
Yeah, their Ablation Studies showed that a simple process reward was too subjective, and a code reward just encouraged it to write code even when it wasn't needed. The weighted consistency approach worked best.
Okay, that makes a lot of sense. Right, let's get to the proof, the experimental results. This is where we see if time actually delivers. What did the benchmarks show?
Across the board, pretty much. They tested on nearly 20 benchmarks: perception, reasoning, general tasks. Time showed significant, consistent gains. What's really striking is in perception. The 7B parameter time model often outperformed much larger models, like the 32 billion parameter Quen 2.5 VL.
Wow, so just making the base model bigger doesn't automatically solve hard perception problems. Time's interactive approach, this test time scaling, actually helps more.
For perception, yes, it seems so. For reasoning, time also helps significantly, especially by letting the model offload complex calculations into code. Though they do acknowledge reasoning still relies heavily on the base model size and inherent knowledge. Time helps by improving the visual input quality and handling computations the base model might struggle with. And generally, it showed solid gains, including a noticeable drop in hallucinations.
And looking closer at perception, that MME real-world benchmark, the impact was biggest on the really hard tasks, wasn't it?
Absolutely. Where the baseline model struggled, time shone. Like in monitoring tasks, perception scores jumped over 27%, and reasoning scores went up by a massive 81%. Similar story for autonomous driving scenarios, perception up nearly 65%, reasoning up over 33%. Huge gains on the tough stuff.
But less improvement on tasks that were already easier, like basic OCR or diagrams.
Right, which really highlights time's strength, tackling the complex visual challenges where standard MLLMs often fall short.
And the Ablation Studies backed up all those design choices. The SFT strategies, the reward function.
Yep. They showed that just doing naive SFT without their careful data curation and training techniques was chaotic. Masking the sandbox output, training on the last round, annealing the math data all proved essential. And the consistency reward structure was confirmed as effective, while simpler process or code rewards weren't helpful.
And they saw the model get more efficient during RL training, using less code for simple tasks.
Exactly. The average response length went down, suggesting it learned when code was actually necessary, rather than just using it all the time. It got smarter about applying its tools.
So it learned efficiency and correctness.
Pretty much. The result reward went up, showing better answers overall, and the consistency reward increased significantly, meaning the reasoning became much better aligned with the final answers. It learned to show its work properly, you could say.
Okay, this is all very promising technically, but let's make it concrete. Let's look at some case studies. How does time actually behave in practice? Cropping and zooming first.
Yeah, they have some great examples. There's one with a street sign image. Time figures out the sign is small, far away, decides to crop and zoom, generates the Python code for it, runs it via the sandbox, gets the zoomed in view, and then correctly reads Michigan.
That's a perfect illustration of the whole process. Deciding, coding, executing, answering.
Right, and another one reading a phone number written vertically on a building. Same process.
Yeah.
Analyzes, decides to crop zoom, codes it, executes, reads the number accurately. There's also a neat case where it's asked to count awning tricycles. It zooms into the likely spots, but then correctly concludes there aren't any, which shows it's not just finding things, it's reasoning about presence and absence.
Understanding absence is definitely a higher level skill. Okay, what about rotation and contrast? Those seem like common real-world issues.
They showed examples there too. One involved a formula written at an angle. Time recognized the slant, generated Python code to rotate it. Interestingly, it figured out the angle needed from the file name, not just the image, and then correctly read and formatted the formula in LaTeX.
Using metadata like file names, that's clever too. And contrast.
Yep, an image where text was hard to read due to low contrast. Time identified the issue, generated code to enhance the contrast, specifically by a factor of 2.0, and made the word communities clearly legible. These aren't just small fixes, they're enabling perception where it would otherwise fail.
Definitely crucial for real-world use. And the complex calculations, how does it handle integrating math?
The Goose cooking problem is a good example. It involved setting up a system of equations based on the text description. Time deduced the equations, then generated Python code using log2 and pow functions to solve for the variables a and b. It basically used code as its calculator for complex steps.
So it leverages programming to extend its mathematical reasoning. Powerful stuff. But credit to the authors, they also showed where it doesn't work perfectly, right? The bad cases.
Absolutely. Transparency is good. They showed cases where it didn't use code even when it might have helped, like on a complex high-res chart, though sometimes still got the answer right anyway. And conversely, sometimes it used code for really trivial calculations, like multiplying 0.5 by 9, which just added unnecessary overhead. And in one case, it did that and still made a mistake, mixing up variables.
Huh. Okay, so sometimes overeager with the code, sometimes hesitant. And inaccurate cropping, too.
Yeah, there was an example where it cropped a totally irrelevant part of the image, but somehow still managed to deduce the correct answer from other context. Shows some robustness, maybe, but also that the visual grounding isn't perfect yet. Still room for improvement.
Okay, so wrapping up, where does this leave us? Time's Think Beyond Images approach feels like a really solid step forward. Giving MLLMs these autonomous tools for image manipulation, for computation, it's definitely pushing the envelope.
For sure. And the paper itself points out limitations and future directions. Performance is still tied to the base model Imagine Time, built on an even more capable future foundation model. Plus, they highlight a need for better benchmarks. We don't really have great standardized tests for things like rotation correction or low contrast enhancement yet. That's kind of call to action for the research community.
Yeah, good point. So maybe a final thought for you, our listeners, to chew on. This work lets MLLMs move from just interpreting images to actively interrogating them, like an analyst using digital tools. How could that change how we use AI for complex visual tasks? What kinds of problems could you solve now that were maybe out of reach before with an MLM that can dynamically tweak its own visual input?
It's a really exciting direction. And importantly, for anyone wanting to build on this or experiment, the authors have open sourced everything, the datasets, the sandbox code, the model code. You can find links in our show notes if you want to dive in yourself.
Excellent. Well, that wraps up our look at the Thyme paper on AI paper podcasts. Thanks for tuning in, and we'll catch you on the next one.